Yeah, it works. So let me first say a few words about what is our main challenge in speaker recognition, why we say robust speaker recognition. The main challenge there is the channel or session variability. What do we mean by...
I'm assuming when you say this, it's the only challenge, right? The challenge is variability, which is comprised of two parts. One is the channel and the other is the session, right?
Did you see George's name on that title slide?
This doesn't seem profound, but I don't know.
Well, let's leave this for the discussion part. So why this is challenging in speaker recognition? In other domains, I mean, like even speech recognition or language identification, whatever, we usually have enough data to train our models of our classes, while in speaker recognition, we usually have just limited amount of data to train the speaker model, and then we have another data that we are supposed to say whether those data come from the same speaker or not. And these data can actually come can be recorded under different conditions, can come from different microphone, from different acoustic environment, can go through different transmission channel, landline phone or cellular phone, and the speaker can speak in different style because of aging, mood, so can speak different language. And then there would be the mismatch between the training data for training the speaker model and the test data. And the system can have problem with that. It can start recognizing the channel instead of the speaker itself, also. Just to show you how serious the problem is, this is picture from 2008 NIST evaluations, where we show performance of two systems, on two conditions actually. So the same system, but on two conditions. In one case, there was a condition. There was a condition where each of the utterances that we were supposed to compare, whether they come from the same speaker or not, which is the task here, they were always recorded using the same microphone. In the other case, they were recorded or could have been recorded also using different microphones, and you can see the difference in performance. We are showing the performance on that curves. Actually, I should have put here what's going on here. We have the probability of false alarm and probability of misrejection, or so basically detecting that is the same speaker which wasn't actually the same speaker, or missing that trial where that was the same speaker. And then we have some curve which is actually telling us some well, on the curve we have different operating point, and then we can ask if the probability of false alarm is this much, how much of the correct utterances or correct segments of the same speaker we would miss. And of course, the closer this line to the beginning is, the better performance of the system is. What we will, throughout this presentation, usually show the results on is just, if we show just a single number, we would be showing just this position, which would be just single value. We call it equal error rate. It just says what the error is if we say that both kind of errors have the same importance. Sometimes people would show something called DCF, which is just another point on the same line. That is just for considering different costs associated with those two kinds of error. So if both these numbers become smaller, then it means that the system is performing better. So this is just how to interpret the results that will be shown later on. So in this case, this system is doing about 3 times more error than the other system. And all these errors are actually just because of the mismatch in channel. So or mismatch in microphone. So the channel mismatch is quite serious problem. Oh, okay, it's fine. So we have actually figured out that we are not the only one that have the problem with this unwanted variability in the data. So I can show you another example of somebody else who has that problem.
Why am I here? Your life is the sum of a remainder of an unbalanced equation inherent to the programming of the matrix. You are the eventuality of an anomaly which, despite my sincerest efforts, I have been unable to eliminate from what is otherwise a harmony of mathematical precision. While it remains a burden assiduously avoided, it is not unexpected and thus not beyond a measure of control, which has led you inexorably here.
So this is actually the reason why we are also here, because we also realize that we can't actually get rid of the unwanted variability, and we also have to somehow get it under control. We just use different tools for that. In Matrix, that they had this agent Smith for controlling the unwanted variability. We have the joint factor analysis model that you will hear about a lot during this presentation. Just to show you that the system based on joint factor analysis that I will explain thoroughly later on, the system gives quite a good performance. This is an example of performance of the system from 2008 NIST evaluations for the condition where both the training and test data come from telephone data. And these are dead curve of all the participants in the evaluation. And actually, at least in this condition, the best performing system was basically based on joint factor analysis. And you would actually see that some of the other best performing systems were also based on the same system. So this is the state-of-the-art technology that we were working on here, and we were trying to extend it somehow. Those of you who don't know what the NIST evaluations are, this is the evaluations organized by National Institute of Standard and Technology, and the systems of different teams are compared using common paradigm. And actually, all the participants in this workshop that were in our team participated in last NIST evaluations. So we found this JHU workshop to be very useful for us. That provided us great opportunity to do the common post-evaluation analysis of our system and combine and improve techniques that individual sites have developed. And thanks to NIST evaluations, we also had identified some problem that we wanted to work on here. We had a well-defined setup and evaluation framework, and we had our baseline system that we could work on already. And we actually split into 4 subgroups for this workshop. Each of those subgroups worked with this joint factor analysis system, so we all could share ideas, but each of these subgroups worked on a little different problem where they applied the joint factor analysis model to solve different problems. So first subgroup was the diarization group. So the diarization is important problem for multi-speaker speech applications. And at one level in diarization, we have to actually accurately discriminate between speakers. And we thought that joint factor analysis, which has to be extended somehow, and we will hear how that must be extended, would be the right tool for doing that. And so the goal was to apply diarization system to some telephone and speech and interview microphone speech, which are actually 2 conditions also in NIST evaluation. There is some condition where you need to first do the diarization and then to do the speaker verification after you have identified where each speaker is speaking. And there were 3 people from 3 sides working together, combining the technology that those 3 sites already had developed, and they also applying the new ideas, using the factor analysis in speaker diarization. The second team was concerned about extending the factor analysis model by conditioning. So the problem is that we believe the factor analysis model is not optimal or suboptimal for different conditions. Where different conditions, we mean segments of different duration, different phonetic content, or different recording scenario. and that it would be good to extend the joint factor analysis model somehow so that we condition the joint factor analysis model on these conditions. And they have explored two approaches. One was building separate factor analysis model for each condition and then combine things at the end. The other one was, in fact, the joint factor analysis tries to directly model the unwanted variability or the channel or session variability. So they try to extend the joint factor analysis model so that it actually explicitly models this variability given by the condition, these new conditions. The third team played with combining joint factor analysis and support vector machines. And so combining the joint factor analysis and support vector machines. Support vector machines proved to be very useful for speech recognition, speaker recognition, and what we did there, we used parameters of generative speaker model, like GMMs, modeling speakers as features for support vector machines, and we knew that joint factor analysis actually provides very high quality speaker models, but using those models, the parameters of these models as features for support vector machines hasn't been useful so far. So the goal was to analyze this problem, to redefine support vector machine kernel so that it starts working with joint factor analysis models, and also the application of joint factor analysis vectors to recently proposed and closely related bilinear scoring techniques. Well, that was the third goal, which should allow quite fast scoring with joint factor analysis models. And the fourth team was team working on, where I was actually in, was the team working on discriminative training of factor analysis models. Discriminative training proved to be useful for different tasks. In speech processing, was speech and language recognition gives quite a lot of improvement. But in those tasks, again, we have lots of data to train model of classes. In our case, again, we have the problem that we have just limited amount of data to train model of classes, so we can't apply the discriminative training as is to this domain. So our goal was to reformulate the speaker recognition problem as binary discrimination between target trials and non-target trials, or in other words, in pairs of recordings that comes from the same speaker or that comes from two different speakers, and then discriminatively train system, the whole speaker recognition system, to separate between these classes. So we will hear more about that. At the beginning, let me give you just a quick tutorial to what joint factor analysis model is. The other teams are going to explain how they extended the joint factor analysis model and how they used it. So let me just tell you, let me give you the first fast tutorial what the joint factor analysis is and how we should understand those different parameters of the model. And let me start just with what we did long time ago with relevance map adaptation, and we will see how that is related to what we have done already in the past. So relevance map adaptation, for simplicity, let's just consider two-dimensional features. Let's, for simplicity, model things just be single Gaussian. We usually use Gaussian mixture model for modeling the data. And we take data from many speakers, train some common model, universal background model, or we call it UBM, to model all the speakers, and then getting some training data for some particular speaker, we adapt this model towards the data. The intuitive interpretation of relevance map is just we move the mean, and we actually adapt only mean parameters. So we move the mean of the Gaussian towards the data. More data we have for the particular speaker, further we move the Gaussian. If we have plenty of data, it would just equal to, or infinity of data, it would just equal to maximum likelihood retraining of the model. And we get a speaker model. Now we get some test data, and we can decide whether it's closer to the generalized speaker model or whether it's closer to the target speaker model. In this case, we would probably decide that the data comes from UBM. It looks like it's closer to the UBM model, not from the target speaker model. But what if that was actually the same speaker? What if these data are different just because of the difference in the channel, because of the unwanted variability that I was talking about? So what if we trained another model on those data, we would get another model, and possibly this model could represent the same speaker. And if we were getting more and more utterances of the same speaker, we could actually train the whole continuum of models for the same speaker. Then if we took utterances of different speaker, we could train whole continuum of models for another speaker. And now we can actually see that there would be some direction with high intersession variability, that unwanted variability, and some direction with high speaker variability. So in this direction we can recognize speaker, but in this direction the speakers overlap highly, and we want to separate these two directions. Now, if we figure out the direction, what we can do about how we can make use of the knowledge that this is the direction with high session variability. We have the target speaker model, we have the UBM, we have the test data, and say the test data probably comes from the same speaker. If we made decision just based on these two models, we would make wrong decision. We would say anything that is on this side of the decision boundary is closer to UBM, and we would say this is not the same speaker. But what we can do is just to adapt both the UBM and the speaker model in the direction of the high intersession variability. So just move both those models along the direction with high intersession variability. And now we actually see that the speaker model fits quite nicely to the test data, and this is probably the same speaker. So both the red data came from the same speaker. Now, how is that related to the joint factor analysis model? In fact, the joint factor analysis model is just a model that tries to model these different variabilities in model space. So on the previous slide, we worked just with single Gaussian and two-dimensional features. So the speaker model could be represented just by the mean of the Gaussian itself, so it would be just two values representing the speaker model. Let's have here another example, which would be three-dimensional parameter space. So in this case, it could be, for example, we would have GMM model with three components, but just one-dimensional features. And then each speaker model could be represented as point in three-dimensional space. And the joint factor analysis is probabilistic model proposed by Patrick Kenny that we were happy to have in our team also. And the speaker model is then represented as the mean supervector. So in this case, the point in three-dimensional space, but usually we worked with the space of the model parameters as dimensionality, something like hundreds of thousands. And the speaker model is represented by the supervector that is composed of these components, where this is actually the original UBM that we start from and we move outside of the UBM itself. Then we have some matrix V, which defines subspace of the high dimensional space. So in this case, the columns of the matrix V would be just these two directions. And the magnitudes of these vectors actually say how much variability we have in those directions. So in this case, these two directions would specify this plane, and this would be plane with high speaker variability. So most of the speaker variability is just in this plane. Then we have this matrix U. Columns of this matrix U actually defines the plane with high intersession variability. So the variability doesn't come from speaker, but that you can see if you take two recordings of the same speaker. And then we have another huge diagonal matrix D, but just diagonal matrix, and tells us some residual variability in all the individual directions. And that should show us some speaker variability that is not covered by this subspace with high inter-speaker variability. And now, to synthesize the speaker model, we actually do just some linear combination of those bases of these vectors. So to synthesize the speaker model, we have some low-dimensional vectors of weights, this y, low-dimensional vectors of some, we call that speaker factors, channel factors, that is telling us how far we should go along these directions in the speaker subspace, channel subspace, and large dimensional vectors z, which is describing the residual speaker variability. And now, what we can, once we have the model, once we have identified those, the speaker subspace, channel subspace, those variability, I will tell you how to do that in turn. But if we have identified that, how we can use the model. Now we can enroll the speaker model. So given some set of enrollment data and given the hyperparameters, the identified subspaces, we can obtain mapped point estimates or posterior distributions of the factor x, y, and z. And as I said, most of the speaker variabilities, most of the speaker information is contained in the low-dimensional vector y. The remaining speaker variability is contained in the high-dimensional vector z. And x shouldn't contain any speaker information. It should contain only the information about the channel. But as you will see, then some of us actually managed to recognize speaker also out of that information. So this way, once we estimate these factors, they actually define the speaker model. Once we have defined this, we have estimated the parameters for the speaker model, we can test new test utterance. So given the speaker-dependent factors y and z, and we can estimate actually new channel factors for new test utterance. Doing this thing, we actually adapt the speaker model to the test utterance, so it equals to what you saw, just moving the Gaussian in the direction of large channel variability towards the test data. So this is what you saw on the animation, and this gives us the channel adapted speaker model. And once we have the channel adapted speaker model, we can just evaluate the model. We can compute likelihood ratio between UBM and the channel adapted speaker model, and see whether the test utterance is closer to UBM or the speaker model itself. And to be able to do these things, we first need to train those hyperparameters. So the hyperparameters can be actually trained using EM algorithms, where for training the factors are our hidden variables, and we iteratively estimate their posterior probabilities, and then the hyperparameters themselves to maximize likelihoods of training data. And to train those, we just put there some special constraints, so that if we have, for all the segments of the same speaker, the speaker factors y and z must stay the same, while the x factors, those x factors, those channel factors can differ from utterance to utterance, even though that those are utterances of the same speaker. So this is the way how we train the whole thing. And just what you want to remember for the rest of the talk is, whenever you see y, you know that this is some low-dimensional vector with compressed information about speaker. This is something that contains a lot of information about speaker, and some of the team were trying to recognize or compare speaker just by comparing those y's. So just remember that. And let me just go quickly. You may have heard of different versions of actually the factor analysis model itself. We didn't call it factor analysis sometimes. So in fact, the relevance map adaptation that I showed right in the beginning is just special case of factor analysis. If you consider just the matrix D without any channel subspace and speaker subspace, and if you set the D to be fraction of covariance matrix divided by some taus, which is the relevance factor, then you actually end up with a model that the factor analysis model where there is no factor analysis in that, but it equals to standard relevance map. What we did, especially BUT and Speak on Data Voice, Nico Brimmer, what we did in 2006 was simplification of factor analysis, where we used the standard relevance map to enrolling speaker model, but then we applied we adapted the model in the directions of channel variability to adapt speaker model to the channel of test data. So this is another version. Or you can use the factor analysis without without the speaker subspace. I mean, without this speaker subspace and encode the speaker variability just in the matrix D and have the channel subspace. So this was used before by Queensland University of Technology and Leah Avignon. And in this case, the D was again set as for relevance map, or you can retrain the D parameters, which is what Patrick Kenny at CREAM also tried before. Or you can train just the full joint factor analysis model that we have been using throughout this workshop. And just to compare what is performances of those different systems, if you don't do any channel adaptation, just do quite poorly. I mean, this would be that curve, this would be the performance of the system without any channel adaptation. If you start doing channel adaptation, but you don't have the speaker subspace, you don't have the eigen voices in that, then these are performances of those systems. You build a full system also considering those eigen voices. Maybe I just didn't say that on those slides, it was written there. But this direction we call eigen voices. So whenever you hear eigen voices, this is the speaker substrate. These directions we call eigen channels. So having the full system with both the eigen voices and eigen channels, you just do much, much better. Well, so now I invite the other speakers, so it would be Doug. So there will be people coming from these individual subgroups and giving you the information about what they did.
All right, so we'll start off into the diarization group. These were the players that worked on this, and we'll each come up and describe various components out of the system that we worked on. As a brief roadmap to kind of orient you on the tasks that we were working on, I'm going to do an introduction to define what I mean by diarization and the experiment setup, where we use diarization, some applications, how we evaluate ourselves, and the data that we're actually going to be using. Then other parts of the team are going to come up and describe two of the main thrusts we had in building diarization systems. The variational Bayes system that was developed at the workshop by Patrick Kinney was one of the main things we want to do new this year. Then we'll have some of the grad students and undergrad talk about some systems that they've worked on, brought in from outside, and also developed streaming and hybrid-based systems and how they use factor analysis in that. And then I'll wrap up with some analysis and conclusions of what we learned on this and where we think we're going. So briefly, the diarization consists of two main parts. You're really trying to say, where are speaker changes occurring in a multi-speaker speech? And then can I group them together where chunks of this speech come from the same speaker? So really we're doing a speaker segmentation and clustering. And the trick is, how can we go about using techniques to do both of these? Now, in terms of where diarization is used, it's primarily used for multi-speaker speech is what we're going to be looking at, two speakers in there. Diarization in general actually is for diarizing not only where speaker changes occur, but where audio changes occur, perhaps speech versus music and other types of changes. But we're focusing exclusively on the multi-speaker problem. And the two main consumers of diarization, so diarization in and of itself isn't usually the final system, but it's usually a pre-process for some downstream thing. It can be used by humans, so for example, annotating transcripts where people might want to look for speaker changes or where speakers are talking, or providing an overview of speaker activity by looking at an audio waveform. We're actually going to be looking more at algorithmic consumption, where you use diarization as the input, for example, in a speaker recognition system where it's multi-speaker speech. We want to split that into speaker homogeneous chunks of speech, run it through our standard speaker detector, and then choose which score we want to report out, a max function being one combiner that we can use. In terms of how we evaluate ourselves, we again also have two ways we can look at this. One is a direct measure, where we can use what's called the diarization error rate, where if we have reference that tells us where the speaker is talking and where different speakers are talking, we can basically just do an alignment of a reference transcript of the diarization that is telling us the ground truth, and then we line that up with our hypothesized transcript and get three types of errors: a miss, a false alarm, or speaker errors where confusions occur. And this is a time-weighted measure which emphasizes the talkative speakers. So we should keep that in mind when we use it, that if you have one person that talks a lot, that actually can drive your error rate in one direction or another. We're also going to be looking at this in terms of a consumer measure where we want to see what the effect is on a speaker detection system. So we may want to look at how we can correlate what the raw diarization error rate is, but how it actually affects the speaker detection system in a two-speaker input data. Now for that, we're using two types of speech for this. We're going to look at the sum telephone speech, which is conversational speech between two strangers. The two sides are summed together. We actually can do diarization error scoring on this because we have transcripts from both sides where we can get ground truth of where the two different speakers are, so we can measure that. But we're also going to be using it to run through a speaker recognition system at test time where we have models that are trained on purified speech, but at test time we want to see how well diarization can actually help our performance in trying to detect the target speaker in the contamination of another speaker. The second data set that we're going to look at is the interview microphone speech, which Lucas alluded to as one of the tasks new in 2008. This differs from the telephone speech in the sense that it's actually a single recording over a microphone, actually multiple microphones in a room, but the style of the speech is slightly different because it's interviewers. They're actually in the same room. They're not on a telephone line trying to converse over and hold a conversation, but they actually have an interviewer trying to move an interviewee to talk. So you have a lot of interjections, and of course with the microphone changing the acoustics, it makes the signal more challenging to work on. So with that, let me hand it now over to Patrick Kinney, can talk some on the system that he put together, the variational Bayes system.
Okay, in fact, we made three different attempts at this problem of how to bring factor analysis to bear on diarization. And we started off with a classical baseline, which I'll describe here first. This is the standard architecture for the problem as developed by MIT, LIMSI, and Cambridge. It's divided up into three stages. The first part is to detect hypothetical change points in the signal where the speaker identity may have changed. It's not a serious matter if the number of speaker change points is overestimated. That then will divide the file up into a large number of relatively short segments where in each segment a single speaker is talking. The next and perhaps most difficult challenge is to identify, if you're given, say, that there are just two speakers in the file, which segments belong to which speakers. And the traditional way of doing this is a bottom-up agglomerative clustering where you look for segments which are sufficiently acoustically similar that you can confidently attribute them to the same speaker, and you build a tree from the leaf nodes up to well, not quite the root node. You stop at two nodes if you're given that there are two speakers. And then traditionally, there's a final stage where with the two speaker clusters that you've generated, you build GMMs in a more or less traditional way and resegment the data and reiterate that as often as is necessary. So I'm going to describe one approach that we took to the question of how to use factor analysis in this problem. The dichotomy that we're confronted with here is that state-of-the-art factor analysis systems are very, very big. Okay? They have hundreds of speaker factors and channel factors. In practice, they are not useful for online processing of the data. Okay, in order to, you have to process an entire utterance in order to extract the speaker factors and the channel factors, and that requires a hefty dose of linear algebra. On the other hand, if you look at the architecture that I just described, you see that it's based on making large numbers of local decisions, where you're trying to identify if a given frame is a speaker change point, if two 1-second segments should be attributed to the same speaker or different speakers. So it's not clear that the two technologies can easily be married together. And in fact, for a long time, I was stumped by this problem until I came across this PhD thesis that I've cited there by Fabio Valente, where he used Bayesian methods on the speaker diarization problem. And this is actually quite an original piece of work, which seems to have been largely neglected. So I'll just take a minute to explain what are the advantages of adopting a Bayesian approach for this problem. I mean, it sort of goes without saying that in machine learning in general, Bayesian methods have the upper hand, but that's not true in speech, because discriminative methods have won out, and it seems that you have to choose between one or the other. Bayesian methods are generative, and for the time being at least, we seem to be backed into a corner. So as regards this problem, okay, here are some of the advantages of adopting the Bayesian approach. One is that you get convergence guarantees, just as good as in the EM algorithm. You avoid altogether the pitfalls of making premature hard decisions, as in agglomerative clustering, where you pair two segments together that actually belong to different speakers. In fact, this by itself suggested a soft clustering heuristic which we could import into the baseline system, and it reduced the error rate in the baseline system by 50%. And there are some other, at least theoretical advantages that you can cite for Bayesian methods. Essentially, they are intrinsically regularized. They are protected against overfitting. At least that's the theory. Fabio Valente realized that because of this, it ought to be possible to determine how many speakers there are in the file without having to tune the usual fudge factors. In practice, what happens, though, with Bayesian methods is that you usually end up having to tune the prior. So it's not altogether clear that the theory is going to be borne out in practice. But it's really very nice theory. Okay. In the approach I adopted, and as I mentioned, there were two other attempts, okay, which will be described by Fabio and Chip after me, to use factor analysis in speaker adaptation, in speaker diarization. I'll just describe one. So I started from the first two terms in the factor analysis equation, just the eigenvoices. Lucas has already explained how this works. What a Bayesian statistician would make of this is he would call this a highly informative prior on the speaker population, because it is saying that all speakers live in a very low-dimensional subspace of the GMM supervector space. The GMM supervector space typically has a dimension of about 100,000. We use about 300 speaker factors for speaker recognition. Okay, so there's a very tight constraint being imposed by the eigenvoice prior. So here's the variational Bayes algorithm in a nutshell. We're given two speakers. I start by uniformly segmenting the utterance into 1 second intervals. And I alternate between estimating two types of posterior distribution. Let me just skip ahead to describe what those posteriors are. Okay? For each segment, I try and attribute a responsibility for each of the two speakers. Okay? A posterior probability that the speaker is speaking in that particular segment. Okay? When I say I don't make hard decisions, it's a soft clustering, these are not typically 0 and 1. Okay? Although by the time the algorithm has converged, you would expect to see zeros and ones. The other posterior distribution concerns the location of the speaker in the Y space. Remember, we're representing each speaker by a point in this 300-dimensional speaker factor space. Now, we don't know where the speakers are, so we represent the two speakers by posterior distributions. In this case, they're Gaussian. They're specified by a mean vector and a covariance matrix. The mean vector is just the point estimate of the speaker factors, and the covariance matrix, well, you have to imagine it's 300-dimensional. It tells you, well, how uncertain you are about the location of the speaker in the point space. So the way the algorithm works is you start by extracting Baum-Welsh statistics from each of the 1-second intervals. Then on each iteration, for each of the speakers, you'll synthesize a set of Baum-Welsh statistics for that speaker by using the responsibilities that you've assigned to each of the segments. Okay, you just weight the Baum-Welsh statistics in each of the segments by the corresponding posterior probabilities. That gives you Baum-Welsh statistics for each speaker. Baum-Welsh statistics for each speaker, that's enough to update the distribution of the speaker factors, which is your estimate of the location of the speaker in the Y space. Conversely, once you have updated the distribution of the speaker factors, you're in a position to recalculate the segment posteriors, the posterior probability in each segment that the speaker is talking. The final stage is just the same as in the traditional system. We construct GMMs for each speaker from the speaker clusters that we found. We resegment and iterate. And the part about assigning posterior probabilities for each segment to the two speakers, that's something we realized that we could import into the classical system, and we could devise a heuristic in the traditional system and get it to work there as well. That's where that 50% reduction came about. Okay, well, this is really just for hardcore people who are going to want to read this after the fact. The feature set that I used is the feature set that we agreed on for the purposes of doing factor analysis experiments in this workshop. It's not a traditional feature set for doing speaker diarization. And in fact, in the Viterbi segmentation phase, the third phase, I found it was useful to resort to a more traditional feature set, which is just unnormalized Kepler coefficients, C0 up to C12. So I'm not sure yet what the right feature set is to get this type of algorithm working. So Doug described, well, I will just report on diarization error rates, okay, rather than speaker recognition error rates. This is a situation where we happen to know what the ground truth is because of the way that NIST collected the data for the sun-channeled task. So here are the principal results. The baseline system, which was the MIT speaker diarization system, which includes Baum-Welsh re-estimation and Viterbi segmentation, was getting about 6.8%. the variational Bayes in the first implementation got 9%. It was at that point that I realized that the resegmentation wasn't working as well as it should have, and I borrowed the technique that Doug was using. That is, I built GMMs from unnormalized Kepler coefficients, and that halved the error rate for me. It brought it down to 4.5%. Then, having succeeded in running the variational Bayes segmentation, I was now in a position where I had non-uniform segmentation of the data. Instead of 1 second intervals, I could rerun the algorithm with the speaker change points that I had already found, and that gave a slight improvement down to 3.8%. And as I said, importing the variational Bayes soft clustering technique into the baseline system also brought us down to 3.5%, which is a 50% reduction in error rate. The only other thing I would like to say about this is that you'll notice that we are careful to report the standard deviations of the diarization error rate. What's going on here is that on most files, we have a negligibly small error rate. It's 1 or 2% of frames that are misclassified, and then there's about 10% of files where everything goes haywire. Okay, whether it's because the two speakers are particularly animated or one speaker dominates the other, the diarization algorithms tend to break down, and we get these wild errors occurring in some of the files. So my secret hope was that by using this very strong prior information in the speaker factors, we would be able to correct this. But so far, I would say all I've been able to show is that the Bayesian approach pays big dividends. And there's more work to be done on using eigenvoices. Yes?
Did you mention how you computed the diarization error rate?
It's a script that's provided by NIST, which essentially it takes a reference transcription and the proposed transcription. It looks for an optimal alignment between the two and counts the number of frames that are misaligned. It's done, yeah. Yes.
If you thought that voice, people talking at the same time was a serious concern, would you consider having a third model?
Well, I would like to build some extra eigenvoices out of data that is actually fabricated by superimposing two speakers and seeing if that would tackle that problem. But that's not for the immediate future.
You don't know if that's why these files go haywire.
We don't know. It's not counted in the NIST error metric, okay, these overlapping periods, but the algorithm has to cope with this, with these overlapping periods in doing the clustering and segmentation. So it's a plausible candidate for research. Yeah, sure. Okay, so I'll hand it over to Fabio.
I'll describe briefly our stream diarization system using speaker factor, but in another way, like Patrick done with the variational Bayes technique. We use here local decision, and so we have to live in a small speaker factor space. In fact, our V are live in a small space of 20 dimension. And here we create a stream of this speaker factor, and using the stream of the speaker factor, we create clustering, segmentation, and clustering. And this is the overall architecture. We have our audio file, and we divide our audio file in different slices of 60 seconds. and in each slice we perform the streaming factor analysis, where we create some model for each speaker that we found in each slice. In this way, we can do a streaming segmentation. We can do an online segmentation because we don't need the whole utterance. We need only a slice, and in each slice we can do segmentation, and then in each slice we can compare the model that we created, and then we will do the slice clustering. Then we have these two phases that this is the streaming factor analysis. We take a slice, we compute a stream of this speaker factor, and like you can see in this picture, we have here the first two dimensions of these streams of speaker factor, and here we have two different speakers. And you see that we can do a clustering of this speaker factor. We create two different Gaussian for each speaker that we found in this stream, and with a big criterion we can select how many speakers there are. For example, if there is only one speaker, we see that we have to create only one Gaussian. And with this clustering, actually we can do the segmentation, but there is noise in the Y stream. And then we create a HMM model for each speaker that we found in the clustering stage, and we perform a return segmentation. In this way, we can create two GMM model in the classical way with the relevance map adaptation, and then we create these two different models. And in each slice, we can create the GMM model for each speaker that we found in the slice. And the last step is clustering this model that come from each slice. And the idea is this one. We have from a new slice a new GMM model created with streaming factor analysis. Then we search with a Kullbaum library divergence the best similar model to the new one. And if the distance is above a threshold, we create a new model because we suppose that this speaker is a new one and is not a speaker that was in the previous slice. If the Kullbaum divergence is below a threshold, we suppose that this is a speaker that previously spoken in the previous slice, and we adapt with the relevance map adaptation the previous model with the new data that come from the new slice. And in this way, we can adapt in an online way the speaker that we found in our segmentation. Now Chip will describe a new hybrid system that we developed using this idea and a new idea that Chip can describe. Thank you.
How did you approximate the KL divergence?
Here we have a model that comes from a UBM. Then we can approximate the KL distance using the, here we have Gaussian that are aligned. Each Gaussian is adapted with map relevant adaptation, and then we can select, we can perform the classical Kullbaum divergence for each Gaussian that is aligned, because there isn't a closed form with the GMM model, but our model comes from the UBM. Then we have the alignment, and there is a approximation for the KL divergence.
Hello, everybody. As we are running short on time, I'll try to be as concise and as clear as possible. So part of my work here at the workshop is based on two ideas. First, experiments found at NIST laboratory at CNRS, France, found out that by choosing a hybrid approach when doing the clustering, like stopping at a certain point and then building GMM models for each clusters, provides better results than the general agglomerative clustering. And the second idea is an idea found at the workshop by Najim and others, that by just considering speaker factors, so y vectors, we can, and the cosine distance, we can have a very good approximation of the distance between speakers. Okay, so the first method, well, this is, yeah. So the first method stops at the center point, and then from each clusters builds y vectors, and then we compute the cosine distance between any two y vectors, and taking the one that produces the closest distance between speakers. And we are doing this, oh, okay. And we are doing this until we have two y vectors, meaning two speakers. So what's the problem with this? The problem is that we may have a very small y vector, so we may have a very bad approximation of the speaker. And we can get, for example, at 3 clusters with 2 big clusters having a lot of data, and 1 small cluster which is very different from all others. And we finally can have, for example, the situation of combining the 2 speakers together because the small cluster is very, very different. And this is not good. And how we can deal with this? We can just throw out data which is very little because we think that is not relevant. But this is also not good because we lose data. So we have another approach, is that we are doing the agglomerative clustering up to the top, and then we are going into the tree and selecting the clusters above a certain threshold, so above a certain number of frames, at the deepest level possible in the tree. And in this way, we do not lose data, and finally results that show that this second method is the best and has comparable results with the Bayesian diarization system, so 6.8. The hybrid system doesn't perform right well, and the streaming system, so the system described by Fabio, has a very good diarization rate of 4.6. So now I will invite Mr. Doug to speak about the conclusion and the interview data. So thank you.
So now it's Mr. Doug again. So let me briefly just wrap up and try to tie some of this. So as I mentioned at the beginning, we had the 2 measures, the diarization error rate and the effect of that on a speaker recognition system itself. And so what we were able to do is for the sum telephone speech, we wanted to look to see if we could correlate or see if there was some trends of the diarization error rate predicting the performance of a system. As I said, using these diarization error rates is always a question of you dropped as low as you could, you went from 7 to 3.5, but what does that help you do? So that's what we're trying to do here, is plot it. So this is for the summed telephone speech at test time only. It's a system using the factor analysis recognition system, and it's doing the way we talked about of diarizing this utterance, sending it through, scoring it, and taking the max. And what we see here is there's some correlation. On one end, we have where the perfect diarization, where we're using the reference transcripts. All the way up here is to where we do nothing, just run the whole thing through without any diarization at all. And then most of the systems we had worked on, I guess we were trying to, is getting it less than 10%. They're all bunched here. We had one system that we had stopped early to try to get some points in the middle. So there is a bit of a trend in there, although it's sort of fuzzy to tell that there's a strong correlation. If we look a little deeper, zoom in, the scale is quite compressed here. It's only 1% change in the equal error rate. But you can sort of see there is a bit of the correlation, although there's some funny trends that are happening. For example, you can have 2 systems that have about the same diarization error rate, but can have swings in there. Now, whether that's statistically significant or not, we're not absolutely sure about. But one thing is clear is that the diarization error rate in and of itself may be a bit too coarse of a measure to relate to the equal error rate or how it affects it, because as Patrick mentioned, that's a global error rate, but there might be the extremes that start to hurt you, or how it breaks down when it fails may be more important than the total average that comes out of it.
Excuse me, in the previous plot, why didn't you mention that there is, you say there's no clear need, but would you expect to see a need there?
Well, we had sort of hypothesized that one thing going into this, we thought that there might be a case where as long as you got the diarization error rate below some point, that it would be okay, and then suddenly when it got too bad, it would just jump up. In other words, I wasn't clear that we were going to see. We thought that it might be something where it would be pretty low, and then you'd see it jump up radically when the thing started to fail catastrophically on most of it. We didn't see that. Again, it may be that the measure itself is a bit too smooth, or we haven't really gotten points in between. Or maybe there's no need.
Could it be that you're sort of not measuring the right thing with diarization error rate? Because for equal error rate, every speaker segment is one token.
Yep.
Right? And you get it right or you get it wrong.
Yep.
Right? And in case of verification, you either verify it correctly or you
Yep.
go false. But now its length plays a role in the diarization error.
Yep.
So don't you want to just reweight your diarization error token-wise and then see if there's a trend?
Well, what's a token then?
The reference tokens.
I guess you can't, no matter what the time is.
Right.
Yeah. I mean, that's the true. We might want
The
to...
reference token was assigned to
Yep.
one speaker, you're good. If it was assigned to two speakers, you're bad.
Although it's biased towards time, and you really want the longer segments to be pulled out. Right? You don't want to count a half-second chunk to be the same as a 2 or 5-second chunk. And
No,
if
but
you-
when it comes to equal error rate, whichever you get wrong, it's still counts.
I know, but they're two different. You can't. I'm saying if you try to quantize it there, you're going to take a half-second chunk and in diarization and say that's the same as getting a 10-second chunk wrong.
Right.
And that's not right. I'm willing to get rid of the half-second than I am the 10. But I agree with your general point. Is it the right measure? Is it too coarse? That we don't know. We just took the two and wanted to see the trends. So the next thing that we want to move to, and in fact we have, although we haven't really digested the results as we're doing in our experiments, is moving to the interview speech. And part of our analysis in looking at it is it differs, as I already alluded to at the beginning, in two main thrusts. One is the audio quality is vastly different. There's 13 microphones around in this recording. We work on one microphone at a time. Some are lavalier mics that are very good for the close talking speaker. Some of them are wall-mounted mics, so you actually have distant microphone effects for the two speakers talking, and some of them are closer to the interviewer than the interviewee. So the point is we have variable acoustic conditions, and on top of that, the style of the speech is quite different. The interviewer is really there just to try to get the interviewee to talk, and they inject, and because they're face-to-face, you have a lot of conversational nudges going on where they keep injecting, yeah, sure, and over-talking on top of each other. And in fact, you can see that for the diarization error rate, which is sort of the priors over all the data, that in the telephone speech, it was about a 35% diarization error rate if you just assigned and said this is one speaker for every single utterance. And in the interview, it's 11%, so you know that it's biased toward one person talking most of the time. What we have here, again, is the speaker recognition error rates for two extreme, and this is where the ground that we're going to be trying to address. The ideal diarization in train and test, where we used a lot of side knowledge and information from NIST, and that gives us about a 5.4% equal error rate. And then if you do nothing, no diarization in train or test, you don't fall off a cliff, but you do have a gap, almost doubles the equal error rate. And that's the area where we want to see if diarization can somehow put us somewhere between these two and close in the gap. So with that, let me go ahead and hand on to the last group that's going to be talking before the break on the using conditional factor analysis. And Jason will start it off.
Thank you, Mr. Doug.
Thank you.
All right, so good afternoon. Now, a few of you may know that I delve into a little bit of magic on occasion. So Sanjeev knows with the $20 trick. So if anyone has a spare $20 note, I'd like to give a quick demonstration of magic related to factor analysis.
I'll give you a 5 and a 1.
A fiver would be perfect. Let's go for a fiver.
Okay.
And another one from Fred, thank you. Right, so with factor... All right, so with factor analysis, what we have is a particular direction relating to our nuisance direction, which in this case follows the line of the $20 note. And then we have our speaker direction relating to another direction, pointing in this particular direction, relating to our speaker factors. Now, the interesting thing is factor analysis works really, really, really well until you make the wrong assumptions. And suddenly, when you assume that you were going to get your money back, as one example, that was one assumption. So similarly with similarly for factor analysis conditioning, if you make thank you, George. So similarly for factor analysis conditioning, if you make the wrong assumptions, you're going to land yourself in a lot of trouble. So by the way, speaker recognition team, we have started our funding for the next quarter for continuing our workshop. So moving on from that, I would like to introduce the members of our team who worked on this particular project. That was Sachin from SRI. We also have Ellie from George Mason University, myself, Nicholas from SRI also, and Robbie from QUT. So it is really an international effort on this problem. So factor analysis conditioning, what do we necessarily mean by that? Now, one typical example is that if you look back at the previous NIST evaluations, now some of this may be confidential, but I'm going to say it anyway. The interesting part here is that what I've noticed is that we tend to have a separate factor analysis system for each type of condition. So for the shorter durations, we're careful about how we select our within-session variability, our inter-session variability matrices, et cetera, et cetera. So suddenly we find more and more conditions, we find that we're actually changing our model to suit those particular conditions. So wouldn't it be nice to have something where we could take all this together and model it in a unified way? Fred, you look like you had a question.
I have nothing.
Okay. So that's the goal. So of course we'll go into the introduction. We'll follow on that to say, well, here's the motivation for why we're doing this. So Ellie will give the introduction for that component. We'll then move on to various combination strategies. How do we deal with this issue of handling different training scenarios, different utterance durations, different phonetic content? Moving on to Robbie's work. Nicholas's work was combination strategies. Robbie's work with within-session variability modeling. Myself with hierarchical factor analysis at the end, and then following with a review. So all of these strategies look at different ways we can handle these particular new scenarios. So the bottom line, as Lukash said earlier in his presentation, our problem statement is that a single factor analysis model by itself tends not to be able to handle all circumstances. So we're trying to address this particular problem. So we're looking at it from two perspectives. One where we try to build factor analysis models specific to the problem, and we break that down accordingly, and then perhaps given the application, we then may decide to combine that information at the end. Correspondingly, we would also like to extend the factor analysis model to take account of various other variabilities that are occurring. For example, for short utterances, our hypothesis is that the phonetic variability may be a very, very high contributor to that variation for short utterances. So I'll leave the results and outcomes for later on, but this is here for everyone's reference. And I'd like to lead in by saying, well, each of our team members has looked at the problem from different aspects, but the key aspect here that's common to all is that we're looking at it by breaking the components down into phonetic events and following from there. So with that, I would like to introduce our undergraduate from George Mason University, who's basically been exposed to speech research for 8 whole weeks. We'll give a background on her work. Thank you, Ellie.
Good afternoon. My name is Ellie, and I will talk about detailed analysis on our problem statements. If I can, never mind. All right. First off, I'm going to talk about the effect on phonetic mismatch problem. This is a really extreme example, but it demonstrates very well the challenge that we're having with mismatched phonetic content. Basically, what we're doing is we take the single system, and then we're looking at difference between the content and enrollment data and then test data, and to see how the performance changes. And as you look at in this table, when we have no difference between the test data and the Norman data, say vowel and vowel or consonant and consonant, it gives you pretty good performance. But when we have difference between the test data and enrollment data, such as vowel and the enrollment data, and then consonant and test data, or vice versa, we have a worsened performance. As you can see, equal error rate or minimum DCF increases accordingly. So this phenomena is especially present for the short duration of utterances, because in the short duration utterances, we have a limited information of phoneme contents, phonetic contents, so that it happens more often. Next, what I'm looking at is effect on duration differences. Basically, what we did over here is we used the Hungarian phoneme recognizer, and we extract the phonemes, and then we did some factor analysis model individually. As you see, and then try to compare person speech, which is a duration, versus performance, which you can look at from equal error rate or DCF. Particularly when you look at the phoneme E, it gives about 18% of speech, but because of its high percent of speech, it gives a better equal rate compared to other phonemes. But you can see more in details on next graph. As you can see on this graph, we had nice correlation. So if we have a higher percent of speech, which is longer duration, we had the better performance. But also, I put these 4 different categories we've been focused on. We had these 4 broad categories of vowel, non-vowel, and sibilant, and stop. And I put that information as well, try to see if we can find any interesting observation. What I found out to be really interesting is some of the non-vowels or some of the data was performing better than the other, even though the percent of speech was similar, especially like this one. It was Hungarian phoneme M. So maybe we can take a look at it further in the future. Also, next, what we did is a future analysis. We had the initial hypothesis that when we fuse with two different unlike to unlike, we thought that it will perform better to compare with a fusion with the like to like. So what we did in this experiment was we fused with the vowel and compare with the vowel with others, which is sibilant, stop, and non-vowel, and try to see how the performance differs. And disappointingly, as you see, the blue line is the heterogeneous fusion, which is vowel with the others, and pink is the homogeneous fusion, which is vowel with the vowel. It didn't perform significantly better enough that we can conclude that. And Jason wanted me to say about this joke. I'm not a good joker, by the way, but but I'll say it anyway. But I hope you can laugh. As soon as I got this result, and Jason asked me, so Ellie, what do you think about this result? So I said, it seems like heterogeneous fusion looks a little bit better than homogeneous, but I'm not sure. He said he asked me, can you put your life on that bet? I said no immediately, and he started laughing. Of course, it's not funny. I'm sorry. Anyway, our hypothesis didn't work very well, but during this experiment, we found that the fusion definitely helped to improve the error rate. When we look at on the fuse all, I had about 5.68% of equal error rate compared to the best one we had in the individual was 7.96. Finally, I'm done, and I'll introduce next speaker, which is Nicholas, and he will explain about combination strategy. Thank you.
All right, thank you, Ellie. I'm going to talk about, just checking that this is working. All right. So the perspective we have on this part of this talk is basically when we talk about conditioning the factor analysis, we usually talk about having multiple systems. And when I talk about multiple systems, it can be multiple systems learned on different databases, for example, but being the same system inherently. So that's why I said multiple systems for multiple conditions. During the NIST evaluation, some sites, and most of them, I think, thought that the best strategy you can have is to learn the variability across channel
that match the condition you're actually in. So basically, you could run you could learn a channel variability on the telephone data. And with NIST metadata, you could say, okay, this is telephone. I will remove the channel accordingly. I'm going to choose my model, learned on telephone, and I'm going to remove the channel. And if it was interview data, then you would choose another matrix, choose another system, and say, okay, I'm going to remove it accordingly. This is really a pain, and it shouldn't be that way. We should have a very robust system across varying channels, and that's actually the title of the workshop. So the current solution is, as I said, select the best system for each condition, and this is basically a lot of scripts, or perform score level combination, and this is also not satisfactory. This is at the very end of your system stream. So this is actually our baseline in this sense. We want to go further than that. So the question is how to robustly gather information from this system so that whatever you have as input data, you robustly combine your system and you can run a single system on whatever data you have. So that could be different durations, that could be different microphones. And in our case, we looked at phone variability as an example. But the methodology I'm going to present can be applied to whatever variability you'd like to apply it to. And we chose to explore combination strategies in the model space, and I'll explain that in the next few slides. Moreover, we chose phone as an example, but we chose broad phone classes, and that's there was two main points to choose that. The first one is that you could make a smaller set of events. Say you have two phone classes, you have two systems, and you can play easily with the two of them and combine them together more easily. If you have 58 systems, as many phones as systems, it's going to be hard to produce results. And the second is to work in the speaker space. People usually combine systems because it's different condition in terms of recording environment, so microphone or telephone. And for the workshop, we could take some risk and work in the speaker space instead of the channel space. So here's our baseline results. The only thing you can look at is the baseline is at the very bottom here. These are broad phone classes, so vowels, consonants, and then a further split of consonants in non-vowels, sibilants, and stops. And basically, if you fuse, and Ellie had a lot of experiments like that, if you fuse your system, if you fuse them at the score level combination, you never reach the baseline, although you used, in the end, the same amount of data. So the two classes system, which is vowel and consonants, has 100% of data and doesn't reach the baseline. And this system with 4 classes is even worse. So the hypothesis is that score level combination is suboptimal, and that's not what you should do if you want to have robust systems. So as I said, what we're going to explore is combining systems in the model space. And something that people know in the community, the first method would be stacked eigenvectors. So what is the principle? Basically, you train 2 different systems in, say, telephone and microphone, but for us it's going to be vowels and consonants. And you have those, it's represented by those 2 blocks here. And you train that, and when you run your system, you're going to stack them together. So right here. So that it will produce 2 sets of speaker factors. Several systems, and in our case, it's actually the same system, but different components learned on different data sets, for example. And what we studied during the workshop, it's in different phone class events. So these are represented with V1 and V2. You can imagine V1 is for telephone, V2 is for microphone. Here we use vowels and consonants. It can be anything. This method of stacking eigenvectors, what it basically does, it takes your 2 subspaces you estimated on each data set, each data type, and you stack them together. So if originally you said, well, my speaker can be represented in a small space of, say, 100 factors, you're actually doubling this number. That's why here, whoa, let me go back. That's why here we have 2 y's, so you double this low-dimensional space. And it's true that for whatever condition you're looking at, it's going to be redundant space. That is very true, but we hope that the correlation between spaces will give more information than just running 2 systems and do score level combination. There are really nice advantages of this technique. You don't have to retrain anything. Once you have your 2 matrices here, the V matrices, you don't have to retrain. You just concatenate them and run your system. You don't need labeled data. That's important. If you train on different data set, you don't have, during testing, you don't have to look in the audio file what kind of data it is. If it's, so for example, for us, vowels or consonants or microphone or a telephone, you don't need labeling. And it actually increased the robustness of the system in both scenarios because of the correlation between the subspace. I'll present the results at the very end. The first question that we'd like to ask ourselves, if we work with phone, are we looking at channel compensation or are we looking at speaker modeling? Very easy experiment is to do the following. You compare your baseline where you have a system where you stack the U's, so you stack the channel spaces, and the other one you stack the V's, where you stack the speaker spaces. And you compare that, and you can see that if you all your efforts, I don't know where the damn thing is, if all your efforts are concentrated in the speaker space, then you have a good gain in performance. On the other end, if you look at the channel space, you have a hit in performance. So this is probably characteristic to the phonetic event that we're studying. If you were looking at microphone, it would be the other way around. So that's interesting. And we also like the phonetic events because we hope like this to replicate the behavior of systems such as phonetic GMMs or MLLR systems. The other technique, so you can see it as a Lego study, kind of. The other technique, we could call that augmented eigenvectors, where basically instead of stacking them together and augmenting the rank, you stack them the other way around. What you do in practice is that you increase the model size. You concatenate the supervectors. So you increase the model size, you double it. And the value of the subspace, the rank of the subspace is the same. The disadvantage is you have to retrain the joint variability of your 2 classes, or 4, if you have 4, to make it work. And also, if you want to extend that to 58 classes, like the Hungarian phone set, it's unthinkable. The dimension really is too high. The interesting thing about this is that it's close to the technique called tied factor analysis, because whatever set you're looking at, you're going to produce a single Y. And we found out that the single Y can be generated by either V1 or V2 in this case, and they're going to be very close. And what I've just said, saying that you could generate, you're actually generating only one Y with 2 matrices, and if that you were generating 2 different Ys with 2 matrices, they would be very close. That means there's an error there. So when you generate a common Y for all conditions, in fact, you're generating different Ys for every condition inside your algorithm, and then you average it out. But you don't really see it. So we try to take profit of that by saying we're untying the model. There's always a between class error. That's exactly it. And then you average it out during when you estimate your speaker factors. So in practice, what you do in training, you do the augmented technique. You stack them together and you produce only one Y. But when you want to describe the speaker, you untie it, meaning for every condition you're going to look at what kind of factors you're going to be generating for each and every condition. It's still a single system. I want to emphasize that. You're doubling the rank in testing, but it's still a single system. And on this, we couldn't run it on phone sets for various reasons I'm not going to explain, but if it's really easy to use it as on Gaussians as classes. I mean, you could always consider your GMM, if you have 512 components, as a 512 phonetic event recognizer. And this is very promising. So results, take-home message there. We have few baseline. The top one is the single system, the baseline that people are using. The number of classes on the left. So if you do system fusion with 2 class or 4 class, you're below the baseline. And then you use this technique of stacking. And you can see that you're better than the baseline, but actually you're equivalent. So you manage to reach the baseline with this technique. So it seems that score level fusion was suboptimal. And by taking care of cross-correlation between your data sets, or here the phone sets, you manage to reach back the baseline. Then another interesting experiment is you still do the stacking, but in recognition, you don't use the phone recognition output. So basically, you're not using the vowels consonant knowledge in testing. And in 2 class, it's worse than knowing if you're in the vowel space or in the consonant space. But in 4 classes, you get better results. It seems that you can generate, it's kind of a V sampling, V matrix or subspace sampling. You can generate more subspaces, very redundant, but you hope that you will describe the speaker more precisely. The augmented version was run on 2 classes, consonant and vowel, and you can see that if you don't retrain it, it performs really bad. And if you retrain it, you're close to the baseline. But you're still worse than the stacking technique. And then this untied version was tried on Gaussian as classes on a 16 split of the Gaussian mixture model, and it gives quite good performance. So this wrap up is kind of trying to figure out how to combine several systems, and I hope it could be applied in a different condition if people want to try for language, for microphone. I hope it's going to be helpful for them.
Why do you have the various font sizes?
Sorry?
The various font sizes, did they represent anything? The font sizes in the table.
Oh, the font size, I'm sorry. Yeah, basically on the blue, I mean, each color is a method. And
I'm asking you about the font.
the font, yeah. Yes. So each color is a method, and in each color there's a big font. And so if you want to do system fusion with 2 classes, it seems that you need only 2 classes to perform as good as the baseline. You don't need to go further than that. However, if you want to just generate V's, so speaker subspaces based on your phonetic knowledge, and then in testing just run your system as usual, then the more classes you have, it seems the better you get. Then I didn't highlight this because it's not as good as the baseline, which is always the case there, actually, compared to score level fusion. And that's it. Was I clear?
I still don't understand why. What does the larger font reflect?
Well, the larger font is the best in the color. Well, it depends on which one. For this one, you mean? For the blue, there's an ambiguity, right? Right. Not at the DCF, but if you could do your.
If you follow DCF, then that principle holds.
Yeah, but they're equivalent. I mean, they're really equivalent.
I see. Right.
They're equivalent. There's a real gap on the green side, and the small font on the green side is not as good as the baseline too, which is not true with 4 classes. So in any case, we can go to the baseline and even beat the baseline with some interesting techniques. So I'm going to head off to Robbie for a different subject.